next unit is going to feel like half physics to you. We're going to relate your physics class to the chemistry class. So there's going to be very specific examples of how this relates, and they are just coming straight off the AP exam. So energy can either be kinetic or it can be potential. Kinetic in chemistry is because the molecules are always moving. So get out your molecule hands. These are your molecule hands.
What are molecule hands?
These are your molecule hands. Okay, this is a solid. So a solid, they're in place, but they're vibrating, but they're still moving. They have kinetic energy. Liquid, gas. Okay? That's a kinetic energy part of it. Potential energy comes from the magnets. So it comes from the magnets. When we took the magnets and they attracted each other and they pulled together, that's potential energy. When we flipped it and they were pushing against each other, that's potential energy for molecules. Unit for energy is a joule. We cannot measure joules. We have to calculate joules. Then we learned this graph, which you cannot see me pointing to. So look over here. The Maxwell-Boltzmann distribution graph is the data for the claim that the higher the temperature, the more kinetic energy it has. In science, you cannot make a claim without, well, you can't make a claim without having data to back it up. So this is a distribution graph. It shows, now this is a sketch, it shows that on average, at a higher temperature, molecules have more kinetic energy than at a lower temperature. If they're at the same temperature, it does not matter what it is, it's going to have the same kinetic energy. It doesn't matter how much there is, it's going to have the same kinetic energy. Okay, so we are here in potential energy. It's called energy electrostatic. Electrostatic is the science word for when I say magnets. When I talk about attraction and repulsion, I'm talking about electrostatic. It equals kappa, which is a capital Greek letter K, Q1 times Q2 divided by D for distance. EL, electrostatic. Yeah, that's what I'm doing. Okay, so kappa is a constant, so we're not going to worry about it. Q, it's rude when you talk when I talk. Q1 times Q2 are the charges. So plus 1 minus 1, plus 2 minus 2, plus 3 minus 1. Okay? The higher the charges, the greater the potential energy. So if I take 4 magnets on each side, that is going to be a greater attraction than if I just take 1 magnet on each side. Or if I flip them, it's going to be a greater repulsion. The higher the charges, the higher the potential energy. But it's inverse to the distance. The shorter the distance, so the shorter the distance apart from each other they are, the greater the potential energy. Okay? Because if I held magnets out this far, they're not going to attract nor repel. But if I hold them really close without touching, you can feel them pulling and pushing away. So the kinetic energy is in the movement. The potential energy is in the electrostatic potential, which is the science word for magnet. Okay? The first law of thermodynamics says that energy cannot be created nor destroyed. So put a box in a box. The inside box is called the system. The big box is called the surroundings. In chemistry, the system is the molecules actually doing the reacting. in the reaction. In other words, it's the net ionic equation. It's the stuff that's making the solid, liquid, or gas. That is the system. So the H and the OH making the water. Everything else is called the surroundings. Yep, those are surroundings. The water in an aqueous solution is the surroundings. They're not involved in the reaction part, okay? Only the net ionic stuff. Oh, the heat just turned on.
Actually, they
Really?
No.
All of a sudden.
So hot.
Look what you're wearing.
It is so close.
If energy leaves the system, oh, I'm using colors. I'm using red, blue, and purple.
I can see purple. Why do you say purple?
Because I have red and blue make purple, and I gotta make purple for something.
Oh, why would you tell us? I love it.
I went and dug throughout the whole room for all the purple pens I could find.
I love it.
Actually, there is a lot of research that's what they do.
I really don't think colors.
Like by organization. Okay. If anything leaves the system to the surrounding, we call that negative. It's always from the perspective of the system. So if the system loses energy, that value becomes negative. But if the system gains energy from the surroundings, we would make that value positive. Ways it can gain energy. I can put it on a Bunsen burner and get it hot, give it heat energy. I can shake it and give it kinetic energy. I can plug it in, give it energy. Okay? So no matter what we're doing, it's not magic. Energy is going to be transferred. It doesn't just disappear. And it doesn't come out of nowhere. Okay. In chemistry, heat is Q, a lowercase q. We're going to draw 3 boxes. Box 1 plus box 2 equals box 3. To me, red means hot. Does red mean hot to you?
Mostly.
I'm going to start with red. This is going to be a picture of a hot molecule, and it has a long tail on it because it has a lot of kinetic energy. It's moving very fast, which means its temperature is high. The longer the tail, the more kinetic energy. To me, blue means cold. Does blue mean cold to you?
Yes.
Cold molecules have a little bit of kinetic energy, so their tail is a little bit teeny tiny, just like that. They're moving slower. If I took boiling water and I poured it over an ice cube, the energy would be transferred from the one that has greater kinetic energy to the one that has less. The fast one speeds up the slow one. The slow one does not slow down the fast one. Energy flows from high to low. Energy transferred from greater kinetic energy to less kinetic energy. Not the other way around. Not slows down fast. It's just like biology, like osmosis, areas of high concentration and low concentration. For any
Seventh grade.
yeah. Osmosis shows.
Jakes. Double Jakes.
I'm talking.
Slows down.
Okay.
No, not slows.
I was reading the part after not.
So.
Draw a hot one and then draw a cold one.
Greg, you annoy me sometimes.
The energy transfers from the hot to the cold until everybody is medium purple.
Oh, I can't. I'm a purple.
I put out a whole bucket of purple pens.
I gave you a purple. I'm sorry, I didn't give you purple. You're not taking my purple. Yeah, thank you.
All the purples. When everything is at purple, that means thermal equilibrium. Okay? So if I take boiling water and pour it over ice, when everything just becomes an even temperature, they all have the same kinetic energy. They all have purple kinetic energy. That is called thermal equilibrium. Okay, before they start panicking, I'm going to give you time to talk. You have to talk about red long arrows, blue short arrows, transfer of energy, which way, and what it means when everything is purple. Ready, go. Work. If you know from physics, maybe not, that let's say I pushed on this desk as hard as I could to try to move it for like 45 minutes, and if it never moves, I never do work, right? In order for something to be called work, there has to be some movement. Yup. The distance part. Okay, so now we have to figure out a way where chemistry does work. In other words, where does chemistry cause something to move? And they're going to give you one of two examples. Put your hand up. The first example is going to be of a piston. A piston is a cylinder and it has this movable part in it. So this part can go up or it can go down. In a combustion engine, inside the piston is a combustion reaction. A combustion reaction means you are producing carbon dioxide and water gas. This fire. So get your molecule hands out again. If I go from a liquid to a gas, you need to get your molecule hands out. If I go from a liquid to a gas, I'm going to create some kind of pressure that's going to move this piston up. So if it started here and moved to here, now the gas molecules caused work. So in chemistry, gases from combustion reactions cause a piston to move, which is where the work comes from. Work is a form of energy, so its unit has to be joules. We do not have a joulometer like we have a thermometer. We cannot measure energy. We have to calculate it. Okay? So our equation is going to be work equals negative P delta V. Negative P is going to be pressure. A unit, maybe you remember our pressure is ATM. It stands for atmospheres. Delta means change, V means volume. So this is change in volume and it has to be in liters. Yep. That means your work unit is going to come out as a liter atmosphere, which is not a thing. You're going to have to convert it every single time to joules. 1 liter atmosphere equals 101 joules. Okay, when the music starts, talk to your battle buddy about how this picture is showing chemistry doing work.
Right here. You got the last two.
Let's write that though. The hydrogen gas.
That's how nuclear energy is supposed to work. No,
It's the steam.
it's the steam.
Yeah. Causes the piston Okay, so to your brain eyeballs, this is a bubbling reaction. Those bubbles are the hydrogen gas being produced. To your brain eyeballs, a combustion reaction is an explosion. So it releases a bunch of gas and light and heat and all that, but we cannot see anything to our eyeballs. This we would see bubbling. It's producing hydrogen gas. Okay. I'm coloring. The system in this reaction are just the molecules doing the reacting.
What does that say inside there?
And these are hydrogen and oxygen molecules. The surroundings are everything else.
No.
So what I can say is the system did work on the surroundings because the system caused the surroundings to move, which means the system would have a negative work value. Could I do it the other way? Yeah. What if I push the piston down? Now the surroundings did work on the system. Okay. Take a look at this here. I'm just going to make it big so you can see it better. With your beta buddy, talk about this chart and all the things about positives and negatives. Ready? Go. If the system gains heat, it's going to be positive, but it has to get it from somewhere. It's not magic. That energy had to come from somewhere. So what we feel is the surroundings, we are the surroundings, is going to lose heat to go into the system. Losing heat to us feels cold, but it's because those molecules have lost kinetic energy. They're going to move slower, so then their temperature goes down. That's called endothermic. If the other way happens, if the system loses heat, it has nowhere to go but to the surroundings. We are the surroundings. The water's going to get hot. The beaker's going to get hot. We can feel that gets hot. So a negative Q means that it's an exothermic reaction. Now let's go back to this equation here. If I want to know what the total energy of the system is, I have to add together the two types, heat and work. But this is a reading test. Nobody's going to tell you whether it's positive or negative. You're going to have to read the story and decide whether heat is entering or leaving and whether work is entering or leaving. And then you go from there. If we have a negative delta E, we call that exergonic. It's like exothermic, but gonic means energy. If we end up with a positive delta E, that's endergonic. It's like endothermic, but endergonic. It's on the inside. It got colder. Okay, one more, and then we gotta do some sample problems.
That's what I meant. Yeah. Inside.
H, capital H means enthalpy. Enthalpy means heat. As long as the pressure remains constant. Enthalpy is heat as long as we don't, in the middle of our experiment, go to the moon or go under the ocean. So in any case that you are going to read about, enthalpy is the same thing as heat. The unit is going to be in kilojoules per mole of reaction. And that's going to make a difference in our math because it's going to be proportional to the coefficients. And I'm going to show you. Okay, when the music starts, flick back until you find your sample problems. Ready, go. Find your sample problems. I went from some gas molecules pushing it to a pile of powder on the bottom. So now my piston has gone down, but my piston has moved, so there was work somewhere. As the reaction occurs, the system loses 1150 joules of heat. Anytime it leaves the system, that's a negative number. The piston moves downward as the gases react to form a solid. As the volume of the gas decreases, the atmosphere is what pushes the piston down. There's less pressure, so the atmosphere does work on the system. So that's a positive 480. Reading comprehension. Nobody's going to tell you positives, negatives. You have to read. Delta E. Total energy equals Q, heat, plus W, work. My total energy of my entire box, my entire system, is I'm losing 1150 joules negative to the surroundings, but I'm gaining 480 positive joules from the atmosphere. Push your buttons, push your buttons. And then tell somebody next to you what that means.
I said it lost 670 joules.
This is where you have to be careful. What if the question asks how many joules of energy were lost? The answer is 670. However, the question asks, what is the change? The change is negative 670. So you have to be careful of wording, especially if it's multiple choice. They're going to give you the positive and the negative number. You're going to have to reading comprehension. Okay, with your battle buddy, go ahead and do number 2. Reading comprehension. Read carefully. Negative has to be I. I is a positive heat. I, if you math it out, is positive 74, and IV, it talks about it being the exact same. So the one for sure is I. Okay, flip it to number 8. Find number 8. I'm going to show you an enthalpy problem. Find number 8.
Chill, bro.
How much heat? Heat is Q. Q is joules, or you could do kilojoules. Is released when 4.50 grams of methane. Okay, methane is just something you're going to have to know today. Is like day 1 of learning it. Methane is CH4. Just like ammonia is NH3, ammonium is NH4 with the plus charge. Methane is CH4. Constant pressure is just telling you that Q is enthalpy. That we're not going to the moon, we're not going below the water. You have to be able to write a combustion reaction. A combustion reaction means it's going to react with oxygen, and it always produces carbon dioxide and water. Balance our equation. So we start with what we know, 4.50 grams over 1 times in 1. Grams on top means grams on bottom. Methane is 16.05. Due to time, I will not make you push buttons on that. Per 1 mole. Moles on top means moles on bottom. This here is your conversion factor, given. Will be given to you. However, so negative 890 kilojoules, that's 890,000 joules of energy are released. For every 1 mole of methane.
So could it say like per 2 moles?
If this had a 2 instead of a 1, this has to be a 2. That is per mole of reaction. If this said 72, this has to say 72 down there. Okay? Does that make sense? It just happens that it says mole. All right, go ahead and push your buttons for real. Answer the question though. How much heat is released? So is your answer going to be positive or negative?
Positive.
Positive. 250 kilojoules of heat, it's an explosion, is released. The answer to the math is negative 250, but the answer to the question is 250.
Oh, I bet you guts.
Okay. Today is Monday. Wednesday, you have a test in Chapter 4 Learning Objectives. Your quiz practice are due. Your essay lab is hold on. I have for you 10. These are just quick questions. You are learning something for the first time today. When you learn something for the first time, you need to do it a lot to actually learn it and remember it. And there's no way you're going to be able to learn it and remember it before the quiz and test unless you do this. These are just simple problems, more need words, just a couple more of those math things. So at this point, your non-mandatory homework restriction is off. You have to do this stuff on new stuff. Old stuff that you've seen before, I'm not that too worried about it. But new stuff, at least go through it, take a look at it, so you know what you're doing. Because we're going to move on. I think we're going to do lab on Friday.
We don't do all of them, right? You do like a couple?
They're all different.
Brother.